Okay, you tell me, Prashant, when to start.
It is now 50. You can start, and I think it is slowly climbing up to 100.
Okay, so that number.
Okay, very good, very good. Okay, so yeah, let's start. So we are very pleased to have Urvashi Sinha joining us today. So we are very honored to have her. She is one of the only persons in India who is working on long distance quantum communications, and in future we might be able to, courtesy Urvashi, be able to do satellite communications and space communication and those kind of things. So to give it a bit of background about Urvashi, so I've known her for many years. She did her basically masters in Cambridge University, and then she did her PhD from Cambridge University. She finished it in the year 2006. Then for 1 year, she was doing postdoc at Cavendish Laboratory in Cambridge. Subsequently, she went to Institute of Quantum Computing in Waterloo from 2007 September onwards. And she was there and she did a pioneering work where she published a science paper in testing of Born identity. And subsequently, she returned back to India and joined the faculty of RRI in 2012. And she has been there since then, and she is a recipient of numerous research grants and has a large group of students and graduated students who are reasonably well placed. So without further ado, I would hand over the floor to Urvashi, and we look forward to a very interesting talk.
Thanks so much, Chiranjibda, for this very kind introduction. And of course, I would like to thank the organizers of this summer school, Professor Panigrahi and the rest of you. Organizing a summer school, I have given a talk at the 2019 one, which was a physical one at ICER, and that was a great experience. But then this time it is even more special because I do believe that we require that little bit of added enthusiasm right now as a community and as a global community. And the intended audience, again, will be the students and the younger people. And so in some sense, it is great that there is this month-long workshop with very exciting talks so far. I have been in many of them. And it gives us hope that, we are going to look at things in future. It will be a COVID-free, hopefully, world, and there are interesting things to do. Interesting things are happening, and it is a big, positive thing that we are looking at through this summer school. So I think that is something that I really wanted to highlight. Going to my talk, which I would now hope to share, and then Chiranjibda will confirm that you can sort of see the screen and so on.
Yeah, we can see.
And then you can also see the whole, the complete slide. Yep. Okay, yeah. Great, thanks. So, as you might have seen, the talk is on exotic world and the foundations of quantum mechanics, precision experiments and beyond. There is someone else who has the microphone unmuted, and if you could please mute, because you are probably at the seaside from the looks of it. Okay, so what I wanted to talk about, so there have been very interesting talks in this workshop for the last 2-3 weeks, and what I wanted to do in the next 1.5 hours is give you a broad overview of various types of research that we are working on at the Quick Lab at RRI Bangalore. Which is, I won't get into the details of all of them because then, of course, it will become a very focused talk on only one topic. I just wanted to give you a flavor of the, holistic picture that we are looking at. And also, bring home this point that, while we are all very excited right now about various possibilities in quantum technologies, we should remember that these technologies are possible because of the underlying science. Yeah, and so which brings me to this quote, which is a very famous one: "Today's science is tomorrow's technology." And you can sort of see what this is alluding to, this particular quote when it was made. And so this is sort of very important because we have this big national mission which has been announced by the union, by the government last year, and we are all gearing up towards hopefully having it start shortly. And so we have to remember that there is a lot of investment of resources of different categories, human and otherwise, which is envisaged over the next several years in India in quantum. And so this has to be, in sync with the fact that this is not only about the applications, but there is also the underlying science and the fundamental science, which needs to be equally well explored. And so, research in fundamental aspects of quantum mechanics is something which should not be forgotten in the excitement towards the applications, because these are two sides of the same coin. So when we do research in the fundamental aspects, we are actually also having ramifications on the applications, which is the other side of the coin. And understanding things better at the fundamental level is only going to improve these applications. So we are not talking about necessarily, only the philosophical aspects, because that is something that is a wrong connotation that sometimes is made about fundamental research. We are actually talking about understanding things at a precision level so that we can have better applications. And so this is the marriage that I wanted to kind of discuss in my talk today about how we are managing that at our lab at RRI. Okay, what is the big picture? The big picture is that our theoretical understanding of the universe is very incomplete. We don't understand more than 80% of what the universe is made of. Okay, and so this actually has implications, deep implications in various things, including cosmology. So this tells you that with this sort of an understanding, which is actually very, very limited, fundamental tests of various principles, various postulates, theorems is very important, because these fundamental tests will form the basis for the applications which will benefit directly from better understanding of these principles. Okay, and so some of the applications that we are working on include quantum computation, and you have heard a lot about this over the last few weeks, and we have our own take on it, which I will discuss in this talk. And then, of course, quantum cryptography, which is supposed to guarantee perfectly secure communication. So our lab deals with experimental as well as theoretical problems relating to fundamental tests of quantum mechanics, quantum computation, and quantum communication. Okay. So, for instance, this slide sort of gives us an understanding that, I think you will recognize all these applications, and some of them on the right-hand side a bit too much nowadays, with the CT scan and the MRI becoming a little too popular for the wrong reasons right now. And so these are all things which we all identify with, and perhaps we are all using in our daily lives in some sense. And these are, of course, possible because of the discoveries that have happened, which when they happened, it was not with the intention that we would be using them in these high-flung, in these very sophisticated, cutting-edge applications. So when the laser was discovered, it wasn't necessarily with the intention of doing something for the, applications on the right. So that is the idea. So we need to focus on both and have a healthy balance between these as we proceed. And that is the message that I wanted to give. So having said that, what are the fundamental principles which we are going to focus on and understand through our work at our lab? So the first one happens to be the superposition principle. Now, superposition principle, again, is something which has been introduced. And of course, that this is something very, very, peculiar in some sense. And it's something not very conventional. So you would say it's a strange phenomena. So this strangeness of the quantum world actually is, giving us this power that is used in the application, for instance, in quantum computing. So to remind ourselves of the superposition, so let me just see if I can get my pointer to work. Okay, so I think this works. So now, you can, so when you talk about a classical bit, then you have basically two possibilities, like the on and off states of the transistor. So let's say the 1 and the 0. Okay, so this is what we are using right now. The computer that I'm using is based on this sort of transistor logic, right? A quantum bit, on the other hand, as you're aware, actually allows for the possibility of many more states. And so essentially, a superposition of 0 and 1 is what is allowed. And as you know, this is represented by this block sphere picture. So a qubit essentially allows you a little bit of 0 and a little bit of 1 at the same time. And so essentially on and off at the same time. And so this is something which gives us the power of quantum computing. When you talk about superposition principle and research in the superposition principle, it seems like we're working on something which is very fundamental and very, at some level, very basic research, right? But that has the exact ramification in quantum computing. So here you have the, single qubit possibility. So in single qubit, you can have 2 to the 1 states, right? If you have 2 qubits, then in the classical scenario, if you have 2 bits, you have 1 in 4 possibilities. But in the quantum scenario, you have 2 square, which is all 4 at the same time. So now if you go on to this number 50, which I'm sure you will hear again from Jay Gambetta's talk, which is going to happen, I believe, shortly, where this 50 qubit quantum computer is supposed to be something that these companies were all focusing on. It was supposed to be something which was the first level of, complex machine that would do things which we wouldn't be able to conceive of in the classical domain. So 50 qubit in the classical sense, 50 classical bits, 1 in 50 possibilities, whereas in the quantum, it's 2 to the power 50. So essentially, this 2 to the power something is what is giving us this access to the state space, which is much, much larger than what we would conceive of reaching using the classical bits, right? And this is happening because of this possibility of superposition of states, right? And so there are lots of devices. You've heard about some of them in this workshop itself, where, and today Franco's talk in the morning, he kind of said that, these devices, some of them may be useful in some applications, some of them may be useful in some other. At the moment, we don't have any clear winner, and all the, different architectures, research is going on at full speed and full force in different labs and industries and so on. And so these are 2 gentlemen who most recently got the Nobel Prize in physics for their contributions to ions and photons, respectively. So essentially, their contributions being at a fundamental level. And so quantum physics is something which perhaps has the maximum number of Nobel Prizes in the last several decades awarded to fundamental discoveries. And these are now being used for these various applications. Yeah. The second fundamental principle, or I would say phenomena, that sort of underlies many of the things that we are doing in our lab is interference. Okay, and so of course you know about quantum interference, but then what you perhaps may not know is that there was a poll by the physics world in this. As you can see, which was about which is the most beautiful experiment in physics. And the double slit experiment actually was voted to be the most beautiful experiment by readers of the physics world in a poll a decade ago. And so why is that? That is, it is summed up very well by Richard Feynman's quote here. We choose to examine a phenomena which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. So essentially, the double slit experiment sort of contains within it all the mysteries of quantum mechanics. And so this is something, when you say quantum mechanics, the first thing people talk about begins with slit interference, right? So now, is this something which can still be used for a technological application? And I will tell you, yeah, it can. And so that is something I will also be discussing in my talk today, okay? And so, of course, I think you guys are familiar with the double slit, so I'll skip the video. But this is, how you get these various interference patterns. This is for the single photon case, and so on. The other fundamental principle or correlation that forms the basis for many of the applications as well as studies that we are doing is entanglement. Again, something which has been introduced a lot in this workshop. And as you remember, the Schrodinger's cat actually summarizes the entanglement thing very well. So here we have a cat inside a box, and there is a vial which contains poison. And depending on whether the cat has the poison or not, there is a radioactive particle which will be emitted from the box. Okay, and so that, of course, tells you that if the cat has this poison, then the cat unfortunately dies, and if it doesn't have this, the cat lives. So if you do not see inside the box from outside, you have the state where the cat could be alive and dead at the same time. And so that is a superposition state. So how does this underline entanglement? So here you have this same, this phenomena, right? So you have this cat and it is actually taking the poison, then a radioactive particle comes out of the box. Whereas if it does not take the poison, does not have the poison, then the particle does not come out of the box. So essentially, by looking at the the state of the radioactive particle, you will know whether the cat is dead or alive. So so that is what it defines entanglement. So by measurements on one subsystem, you know what is happening to the other subsystem. Right? And so this is what is an entangled state. So a live cat with the particle inside, and then the particle emitted and the dead cat. So this is your entangled state. And of course, I actually always like to take this example, which is just to give you a holistic picture, which I'm sure you've done a lot of math on entanglement so far. But then if you think about it from this perspective, that entanglement is something which gives you more than the sum of parts. So this is an orchestra. And so if you listen to the various pieces of music separately, then, it's of course beautiful. But when you listen to them together, then you get an understanding of the piece of music that you're supposed to be listening to. Okay, and so together it creates something which is more than what the individual parts creates. And so this is what we are using in many of our studies and applications in our lab. Okay, and in fact, so this is another example of how these fundamental studies and technologies are so interconnected. So this is something, there's a blog by the Institute for Quantum Information and Matter at Caltech. And this blog article, very interesting, especially for the students to read. So this is Bell's inequality 50 years later. Okay, and so by John Presque. And so, this happened, this was written by him in 2014, which was the 50th anniversary of this paper on the Einstein-Podolsky-Rosen paradox by John Bell. Okay, and so he talks about what the paper is about and so on. But then this is an important part of this blog. So why is that such a big deal? Bell showed that a quantum system is more than just a probabilistic classical system, which eventually led to the realization that accurately predicting the behavior of highly entangled quantum systems is beyond the capacity of ordinary digital computers. Therefore, physicists are now striving to scale up the quote-unquote weirdness of the microscopic world to larger and larger scales, eagerly seeking new phenomena and unprecedented technological capabilities. Okay. Now, this is an interesting paragraph. 1964, when this happened, was a good year. Higgs and others described the Higgs mechanism. Gell-Mann and Zweig proposed the quark model. Penzias and Wilson discovered the cosmic microwave background. And then John Bell saw the Beatles on the Ed Sullivan show. Okay. So now so what is special about Bell then? Many things happened in 1964. Okay, it's very interesting. So Bell's legacy is that quantum entanglement is becoming an increasingly pervasive theme of contemporary physics, important not just as a source of a quantum computer's awesome power, but also as a crucial feature of exotic quantum phases of matter, and even as a vital element of the quantum structure of space-time itself. 21st century physics will advance not only by probing the short distance frontier of particle physics and the long distance frontier of cosmology, but also by exploring the entanglement frontier, by elucidating and exploiting the properties of increasingly complex quantum states. Okay? And so essentially, when John Bell actually submitted this paper on the Bell inequality, I'm sure he did not. Of course, we can't ask him now. That will be really spooky action at a distance. But then I'm sure he did not realize that, this will be the ramification in the 21st century. Now, 50 years later, how pervasive Bell's inequality and Bell's legacy has become in various branches and so various frontiers of physics. And this is a very nice statement that, sometimes Preskill wonders how the history of physics might have been different if there had been no John Bell. Now, without Higgs, Brout, and Englert and others would have elucidated the spontaneous breakdown of gauge symmetry in 1964. Without Gell-Mann, maybe Zweig could have come up with, the quark model. Without Penzias and Wilson, Dick and collaborators would have discovered the primordial black body radiation at around the same time. But it's not obvious which contemporary of Bell, if any, would have discovered his inequality in Bell's absence. So this is the point. So then this was a phenomenal discovery. And in fact has ramifications in almost everything we do now. Not so many good physicists were thinking about quantum entanglement and hidden variables at that time. And so without Bell, the broader significance of quantum entanglement would have unfolded quite differently, and perhaps not until much later. So we really owe Bell a great debt. So this sort of summarizes the theme that I wanted to take in today's lecture, that, there are these things that we do, which, of course, when we work on them, I'm not talking about we personally, but then as a community, when we work on them, we don't always think about exactly which application it will be relevant to. Sometimes it's obvious, sometimes it need not be. But then precision things always tend to have ramifications in applications sooner rather than later. And so this balance is something we would really like to encourage, and that is what we are doing in our lab. So this brings us to, what have we done regarding this theme? What are we doing, and what do we want to do? Okay, and so this is our lab's website. So, I mean, of course, I wouldn't be able to cover 1/10 of what we do in the time that we have today. So please do have a look to understand, and if you're interested in details of various things that I will be talking about. Okay, and of course, as I always say, that it's great that we have this lab, and we're doing such interesting things. At least we believe so. But then it would be pretty incomplete without all these people, who are contributing to it. And so essentially, PhD students, postdocs, scientists, and different types of young, enthusiastic minds who have contributed earlier and who keep contributing to what we do. And that is what, we believe is the way forward to have this enthusiasm retained. Yeah. And so this is how various experiments look in the lab when the students are really particular about taking pictures. Otherwise, you will have lots more screwdrivers and things hanging around. But then, it'll be great when we come to a more offline world where people can actually come and visit us and so on. Okay, and so what we do, the underlying technology that we are using in various science and technology, explorations is to do with photons. Okay, and today morning we heard Joey give a talk on photons. So I'm sure you learned quite a bit about how to make photons from that one. Okay, and so this one again is a review article. In fact, in the 2019 workshop that I attended at ISA physically, this is something I actually discussed a lot in detail at that time. But then at that time, it wasn't quite out yet. So now students can actually read this hopefully and gain some perspective on different types of photon sources. So when we started the lab in 2012, we were one of the first labs to be working on the applications on making these photons, okay, and then entangled and otherwise, and doing various things with it, fundamental and applied. And so this gives you an overview of that. And as we have seen before, so this is the famous down conversion cone. Okay, so these two are the cone, the rings of down conversion. So then if this is the horizontally polarized, then this would be vertical. And if this is vertical, that would be horizontal. So at this point, at the intersection point, we do not really know which cone it belongs to, the photon. And so it could be either, and that is what defines the entangled state. And so we have projects in which we are working with the entangled states, and some in which we are not really working with the entangled states, but more with the heralded photons. So where, these photons always come in pairs, right? As we heard before also. So they come in pairs. And so if I measure one, then I know of the presence of the other because these two are born at the same time. So almost that is why they are called twin photon sources. Because, but then a little bit unlike the human twins who come one after the other, obviously they can't come together. Here they actually are produced at the same time. So by perfectly measuring one of them, we would know of the presence of the other. We don't need to measure it. We can then use it for our experiments. Okay, and so that is called a heralded photon source. So now going on to the various things which I will be actually discussing some of them in detail. This is a snapshot of various fundamental tests that we have performed on quantum mechanics. And in fact, this entire thing is summarizing the work that we have done on the superposition principle. So, I already introduced that. So that was with a reason, because I will be telling you a little bit about our work on the superposition principle, both theory and experiment. Okay. Here we have a snapshot of one of our experiments in fundamental quantum optics, again, something which has a ramification in long-distance quantum communication. Okay. These are our, some of our studies on entanglement and its dynamics. And this is very fascinating. This one I won't discuss much in detail, so I'll tell you a little bit now. So we are working on an experiment which is almost over now, in which we are trying to hold on to entanglement for longer. Okay, so now entanglement is a resource. Entanglement is important. This I think you guys know by now. But then, of course, entanglement is a correlation. So these particles which are entangled, the states which are entangled, they are also interacting with the environment, right? And so this interaction with the environment will bring in decoherence. And so the entanglement will also decay with time. And so this is called, so this is the dynamics of entanglement. And that actually, for certain classes of states, leads to what is called the sudden death of entanglement. And I think Namita gave a talk on this yesterday, I believe, on some aspects that she has worked on during her PhD. And she's currently also working with us on a project on understanding decoherence in certain classes of entangled systems. And Prashant is our collaborator there. So then now the point is here, if the entanglement suddenly drops to zero, it's called sudden death, which is what happens even in human life. Suddenly, if somebody passes away, that is sudden death. But then in case of entanglement, as in human beings, we don't want this to happen. We want to hold on to it for longer so that we can use it for whatever it is that we have made this resource for. And so there we want to manipulate it and either make it not happen or happen much later. And so this is the dynamics of entanglement. And in fact, you can have a look at some of this work here. And the experiment is now done almost. And so we have been able to show for the first time how we can actually delay or avoid sudden death of entanglement using this very interesting photonic system, which gives us a very good control on the problem, because unlike atomic systems where time is actually a factor, right? So the atomic systems, the two-level systems, you have the excited state, it drops to the ground state in finite time. So that, that is actually a process which is time dependent. But in a photonic scenario, time is something you can mimic by using polarization. Have a look at this to understand better. And so you have complete control. And in some sense, this is a proof of principle experiment, which will, set the path for the time-dependent experiments in future. Okay. And so this brings us to the importance of photons in some sense. Photons have been the test bed for many fundamental experiments in quantum, simply because, there are many things which one can do with photons which are actually harder or just require a lot more resource to do with some other system, but you don't gain much. So in terms of proof of principle experiments, photons definitely have a very important role to play historically. Yeah, and so this is something we have just about finished. The other thing is on generalized measurements or weak measurements. I think there were some talks on this as well as we went along this workshop. And here, again, I won't spend too much time here, but then one of the interesting things that we are currently working on is what is called the quantum Cheshire cat. And so the idea being, if you have read Alice in Wonderland, where there was this cat who was separated from his grin. So you have the cat without the grin and the grin without the cat. That's called the Cheshire cat itself. It's a fairy tale concept, right? But then in quantum, it actually means something. So the quantum Cheshire cat is a phenomena by which you can separate the cat and the grin. And in this case, of course, the cat will be some particle and the grin will be some property. And so a loophole-free demonstration of the quantum Cheshire cat has not been done so far. And so we have, again, just about wrapped up a first loophole-free experiment on the quantum Cheshire cat. And I think my collaborator, Professor Holm, is also in the audience here. So this is, again, we have done some very interesting things using weak measurements where we have been able to measure the expectation value of a non-Hermitian operator. And that is, again, something counterintuitive, because you know that when you measure something in the lab, you measure Hermitian because, eigenvalues are real. So what do you do? So that is where weak measurements come in as a very handy tool. Weak measurement being something which is very, very fundamental, but then comes in as a very handy tool to understand more about what happens to the system between preparation and measurement. Otherwise, if you go about it in the strong conventional measurement, the von Neumann measurement, then if you measure something, then you change the state. And so you cannot really, you don't really talk about the same state anymore in the final measurement step. But here, by weak interaction, which of course means, has a lot of math behind it, which I won't get into now, you can actually, through a statistical ensemble of measurements, comment on the evolution without destroying the state. Okay, and so we have done a lot of interesting work on that over the last several years. Okay. So the first thing that I wanted to discuss a little bit in detail is our approach to quantum computing, which is not really based on qubits, which you have heard of before, but instead it is based on higher dimensional systems, or qubits. Okay, and this is one of our first works in which we have shown how our experimental architecture in the lab is working. Okay, so qubit, as you know, has two orthogonal basis states, let's say 0 and 1. So this is the superposition that you form, alpha 0 plus beta 1. Qtrit, on the other hand, has three orthogonal basis states, say 0, 1, and 2. And this is now going to define your superposition. So if you have a single photon and it is incident on a plate which has some apertures on it, okay, let's say 3 apertures, then the photon can take both, all 3 paths with equal probability if you arrange it that way. And so if once it is incident on it, you don't know which one it will take. So it forms the alpha 0 plus beta 1 plus gamma 2 state, where 0, 1, and 2 are the spatial degrees of freedom of the photon. Okay, so this is one way of generating what are called spatial qubits. And now, why is it important? Why is it interesting to work with higher dimensional systems? Now, if you have followed the trajectory of qubit-based quantum computation, which has been for several decades, right? As I mentioned, this number 50 was the first holy grail that people wanted to achieve. This 2 to the 50 is what we wanted to reach. But then it took several decades for the community to reach that, right? And why is that? That is because, as you increase the number of qubits, you also increase the decoherence, right? So then essentially, it's the example I like to take is that, if you have a small room and there are 2-3 people in that, it's fine. But as you keep on increasing the number of people, beyond a point, they would get into each other's way, and that will lead to loss of coherence, right? And so same thing happens with qubits. So it is difficult to actually just arbitrarily increase the number of qubits without having decoherence setting. And so that is why it has taken so long to actually reach this 50 qubit scenario. Now, for instance, if you had what is popular, I think it's the Euro. I'm sure if there is an Indian student audience, they are definitely following the European football. And so then having said that, and I'm not the expert on football, but then having said that, I can imagine some scenarios which can happen in football. Maybe you can have a win, you can have a loss, maybe you can have some sort of a draw, and maybe you can have an abandoned match because it just goes on forever, it rains, and you just abandon it maybe. So there are 4 possibilities, let's say, in a football match. I would need 2 qubits to actually describe that, right? Because each qubit will have 2 states. Each state corresponds to 1 result. But then now if I had a Q quad, which is a 4-dimensional system, I can actually have all these 4 informations encoded in this one system. So essentially the idea being that by having a smaller number of systems, I can actually have access to the same complexity of state space that I can have with a larger number of qubits. And so essentially it gives me some level of control that, okay, so smaller number, but still the same complexity, okay? And so this is where, that is why higher dimensional systems are an interesting area of research. Of course, they are, I would say the qubit-based research has been happening for much longer. So lots of things have been already solved in the qubit scenario. But in the qubit scenario, there are lots of open problems, both in computing, in communication, as well as in other applications where we may want to put it. So coming back to our spatial qubit scenario, so this is, previous work, and this was one of the works in which I was involved when I was a postdoc at IQC, which was to do with a photonic Q-tree, where we played what is called the Aharon-Weidman quantum game and showed the advantage of using a Q-tree over a classical system, okay? What we have done in our lab at RRI is devised a new way of generating higher dimensional systems, okay? So instead of putting apertures in the path of the down-converted photons, which is what was being done earlier by other groups, what we have done is we have actually put in the apertures in the path of the pump beam itself, okay? And so what that means is that the pump, which is, what is going to go and get incident on your nonlinear crystal, right? So that already carries the signature of the higher dimensional system. So now, instead of this Gaussian pump, I will have a pump which will look like that. This is an actual picture of the pump taken on a camera. So this is the pump beam. And so what we now know is that the pump beam actually faithfully transfers its properties to what we call the daughter photons. You know, we call this the pump photon, and the two photons which are generated, they are the signal and the idler photons, or the daughter photons, for obvious reason. And so these daughter photons carry the properties of the pump with them. And so by modulating the pump beam, I can actually have different sorts of ramifications for the signal and idler photons. And this is what I'm using and what we are using in the lab to generate higher dimensional systems at the pump level itself. And this has many advantages over the other way of doing it, which would be about placing apertures in the path of the photon. One of the advantages is it has higher efficiency. Then also, as you may have learned in some other lecture, that, down conversion, while we of course have the Chi2 process predominantly, but we can also have higher photon number states come in, if we have a strong pump. And that will be a problem for the other way of doing it, which is putting the slits in the path of the down converted photon. Here, we will actually avoid such, complications from any other mode. So we will only be dealing with the pure Qubit mode. And this way, we have been able to generate bipartite Qubits in the lab. So a pair of bipartite Qubits, which are done using this new technique. Okay, and this is how it looks in the lab. So this is what I was saying, the transfer of the profile of the pump to the daughter photon. So if it's Gaussian, the Gaussian gets transferred. But if it is this sort of a profile, then this gets transferred at the detector. So it's very neat. Yeah. And so we have been able to measure the correlation between these two photons. And this is a classical correlation coefficient called the Pearson correlation coefficient. And you can see that the correlation is very high. So when you have a certain Qubit in one, the Qubit in one of the states here, the pair photon will be in the exact corresponding state on the other side. So we have very good one-to-one correlation between the two Qubits, as high as 0.9, which is very good because in experiments you never reach 1, which I'm sure you know. So this is where we were. But then, of course, what have we done after that? So what we see is we have a novel bipartite Qubit system, which is highly correlated in the spatial degree of freedom. And what next? Okay. So while there are spatial correlations, how do we know if these correlations are classical or quantum? Yeah. So we can perform an entanglement witness measurement to certify or not certify entanglement, but we actually went on to do better. So McConnell et al. Actually showed the use of this Pearson correlation coefficient as an efficient measure for entanglement in bipartite pure Qubit system. So we extended this work to effectively use this to both certify and quantify entanglement in bipartite, pure, and mixed Qubit systems. Okay, and this is very exciting that our experiments with the bipartite Qubits show a very good match with our theoretical predictions, and we have nearly maximally entangled pair of Qubits. Okay. But then, and so this is what you see, you have these coincidence profiles. So this is what I mean. So one-to-one correlation. So if one of them is here, then the coincidence peaks exactly at that point. Similarly for the second slit and the third slit. And this is the entire profile. Okay. So this is the signal profile and these are the coincidence profile. Okay. And this is this is the coincidence profile of the focal plane, which actually is a signature of entanglement. So if you measure interference in the focal plane, then it is known to certify entanglement. And that is also something we have shown in the process. But we have actually, as I said, done better. And so the very recent results, which are actually being written up right now, is that we have actually derived the monotonicity relation between negativity, which you know is a measure of entanglement, and sum of Pearson correlation coefficients for arbitrary dimensions, not just Qubit. So now we have a way in which we can determine entanglement monotones in arbitrary dimensions, avoiding quantum state tomography. And today morning we heard from Franco why it is good to avoid tomography, because it just does get extremely messy as you increase the dimensions. And so we have been able to derive these relations between negativity and various classical correlation measures, which is Pearson, mutual predictability, and mutual information. And we have done the first direct measurement of an entanglement monotone. Usually, if you want to measure an entanglement monotone, you have to do tomography and then extract the monotone from that data. But what we have done is a direct measurement thanks to these relations that we have derived. And we have also shown that negativity and entanglement of formation are non-equivalent entanglement measures, which means that if I compare how much is the negativity with respect to the maximally entangled state, what is the deviation? And similarly, if I measure the EOF and measure the deviations don't match. And this is something which may be expected in mixed states of qubits, but in a pure bipartite qubit, this is something which is not necessarily expected. And so this is very interesting because it actually then gives us the first experimental demonstration of non-equivalence of different entanglement monotones in higher dimensions. So kind of lays the ground for many interesting studies which we can do based on this. Okay, and so these are our works which are currently being written up. What next? We are working on diffraction-based linear optics quantum information in collaboration with people in India and abroad. We have already shown that a two-slit system acts as a lossy beam splitter. And so, as you may know, there is something called the Rex-Zeilinger protocol in linear optics quantum information, which tells you that if you can make a beam splitter and a phase shifter, then you can actually come up with all possible quantum gates for a qubit system. And so we are investigating that for qubits and higher dimensions and would continue doing that over the next several years. Okay, so this is a snapshot of the various works that we have done. And this is something which may be interesting for the students. Here you can, this was an invited review in an article that I wrote in Scientific American, where I've given a sort of a holistic perspective on our higher dimensional work. Okay. Now, next I go on to another interesting area, which is on quantum state estimation, again, closely connected with Franco's talk today morning, where he actually talked about using machine learning to improve on quantum state tomography. But what I am going to tell you is that I can use interference to replace quantum state tomography. So either you improve upon it or you replace it. And so what we went on to do, and this was collaboration with Arun, who's at HRI, is we devised a new way of estimating the quantum state, which of course is a very, very important area because you see, for all these applications that we're interested in, whether it's computing, communication, sensing, whatnot, we need to have a good understanding of what is the state we are beginning with. Only then the evolution will make sense. So the conventional way of that understanding is quantum state tomography, right? But then, as we have heard before, and I'm going to say again, that as you increase the dimension, the tomography becomes quite intractable because it actually scales as d square. Okay, so as the dimension increases, the number of measurements you need to do scales as d square. And so what we have done is come up with an alternative technique using interference. So as I was saying a few minutes ago, that can we do something further with interference? Because I wouldn't, that is like a very fundamental thing. Feynman said it contains in it all the mysteries of quantum mechanics. Indeed, we can. Now we can use it as a tool to estimate the quantum state, which we believe is very nice. And so this is what we have done, where we have actually shown that our technique scales as d-1. So instead of d square order, it's d-1. So clearly it's linear and much, much more tractable than the tomography counterpart. And so it's an interferometric method using which an unknown quantum state can be inferred from the visibilities, phase shifts, and average intensities obtained from a number of interference patterns. Okay. So this is essentially a single-shot quantum state estimation tool for qubits. And as you go higher, it is d-1. So as you know, for 2, d is equal to 2, so it's 1. So you need only one set of measurements. But as you go higher dimension, you will need d-1 sets of measurements. Okay, and so this is the idea. Of course, this is, I will not go through the gory details of the theory because I'm sure you can have a look at the paper to figure that out. But then the essential idea being that, this is how you would represent a pure state and this is how you would represent a mixed state. And as you can see, the theta, phi, and mu are the three things that you need to determine, right, in order to determine the state. And so what we are doing is we are determining them from an interference pattern. Okay, and so this is your Mach-Zehnder interferometer. So what we have done is these are the set of operations we do. This is a NOT operation and this is a projection. I'll skip the details, but what you can see is that the intensity that we measure at the end actually depends on these parameters. So you can see the theta, you have the mu, and you have the phi. And so by measuring the phase shift, average intensity, and visibility, which of course are all quantities that you can measure from the same interference pattern, we will be able to derive these three unknown parameters, and then we can reconstruct. We then know the quantum state. Okay, and so we have done this for all possible, in some sense, quantum states. So we have done this for the polarization state. Okay, and so by arbitrary angles of wave plates, we can actually get the whole sphere. Okay, and so I'll skip the details here, but then you can see this is our fidelity that we have for the pure state estimation, and this is for the mixed state, and both are very nice, right? So for the pure state, it is in fact going on to 99, and for the mixed state, it is slightly lower as expected because because of certain details which I'll skip for now, but we can discuss later if you wish, which has to do with the poles and the fact that in the mixed state you also need to determine the mu, whereas in the pure you only need two of them. Okay, and so this is our proposal for how we can extend it to a higher dimensional Qubit. Okay, and so this is a theory part which you can find in our paper. And we can also do quantum state interferography for bipartite pure qubit, not just a single qubit. And so this is 2 settings as compared to 9 settings in QST. And we can also determine the entanglement for a pure bipartite qubit system, again, using less measurements. So essentially for an unknown qubit state, a single shot measurement, QSI can quantify the entanglement within a single setup, and of course has a fantastic scaling advantage over conventional quantum state tomography. But the bottom line is, so now I've told you, it's an experiment where we have actually shown how we can come up with an alternative way of estimating the quantum state itself, and which of course has ramifications in several applications. And what are we using as a resource? It is our good old quantum interference. Yeah. Okay. Next few minutes on superposition. Because I promised you that. And so what do I take you back to? You can see I have a fascination with slits. Yes. So this is my double slit scenario. And I tell you that, okay, I have a double slit system. I have a source. I have a detector. And, I ask you, okay, so what is the wave function when both these slits are open? So if I have a single slit open, let's say the solution to the wave equation is psi A. If I have the second slit open, first slit closed, it's psi B. If I have both open, is it simply psi A plus psi B? In fact, that is what is used in all these famous textbooks, and also we have been using it forever, right? That mod psi A plus psi B whole square gives you the interference pattern. But that's not actually true. If you think about it, these are 3 different boundary conditions. So when you open up both the slits, it's a third boundary condition. You can't just add 1 and 2 to get 3. And if you look at it from the Feynman path integral perspective, Yabuki did that in 1986. So if you think about it, this is the double slit scenario. These sort of paths will also be allowed. These are Feynman paths, okay? These are probability amplitudes. So there will be the straight line paths, which will be the classically dominant ones. And then there will be these, which will be the classically subdominant ones, but they will also be there. Because as you know, in path integral formalism, it is an integration over all possible paths that can be taken by the particle in going from A to B. And so these are the things which will bring about a correction to the simple psi A plus psi B scenario. Okay. But in Yabuki's work, while it was great, it was the first one, he actually restricted himself to, situations which were very, very ideal. So point, slits, Planck length, and so on and so forth. So some of the calculations don't really lend themselves to actual verification through experiments because they just won't scale that way. So something needed to be done in order to measure this because, so far as we are concerned, we are doing a lot of work which is in the experimental domain and a lot in the theory domain, which is directly feeding to the experimental ones. So we want to do something where we can measure this correction, okay? And so in order to measure this correction, we want to measure what is called the Sorkin parameter. And this was, in fact, I was involved in this experiment where we used the Sorkin parameter to test what is called the Born rule for probabilities in quantum mechanics. And in our work, which I'm talking about now, we have shown how we can use this parameter to actually quantify the correction term to the superposition principle because of these, additional contributions, which you cannot just ignore. Because if you ignore them, then they will have ramifications in the applications that you're putting them to, right? And so this is what we went on to do using path integrals. And there was an experiment which was done by Robert Boyd's group, almost in parallel to the experiment that we ourselves did, and where they actually used single photons to show, this quantification for this Sorkin parameter. So this was done using single photons, but using gold film. So essentially using surface plasmons. So a different effect from the geometry ones, which we concentrated on in our theory. Having said that, this was their result. So this is the Sorkin parameter as a function of detector position. And so these blue dots that you see, this is their experimental result. And the blue line is the theory expectation from our theory, which they plotted. And of course, I would say that this is not a great fit because, there is nothing in the maxima, neither is there anything in the slopes. So it is just that they are being able to measure at the minima. And you can also fit it by a parabola, for instance. So this is, of course, nice that this was done. But we went on to do better, actually, using microwaves. And so here you can see how the theory and the experiment scale and match really well. So we have the parameter modulating as a function of the detector position. So this was the first measurement of the non-zero Sorkin parameter using classical microwaves. Okay. The next couple of minutes on fundamental quantum optics. Now, the Hongo-Mandel effect, I'm sure you've already heard of, is something which is used as a diagnostic for single photons. So you have two single photons, they are incident on two input ports of a beam splitter. So then you know that they would either exit one way or the other. So they will not split after that if they are perfectly indistinguishable. Okay, and so essentially, if you have them incident on one side, then of course this is what you get. But then if there are two of them, then what happens is the question, and you can go through the math later maybe. You have this. So you form what is called the 2-0 minus 0-2 state, which is essentially a superposition state, of course. And if you measure the correlation between the two detectors which are detecting them at zero path difference, you get a dip. Okay, and that is called the Hongo-Mandel dip. And so if you have perfectly indistinguishable single photons, then you will get 100% visibility for Hongo-Mandel dip. And in fact, in literature, this is what was prevalent, that this fourth order interference of classical fields cannot yield visibility larger than 50%. As long as the visibility is greater than 50%, no semi-classical field theory can account for the observed interference. So essentially, this 50% was taken to be the threshold beyond which you would have quantum effects. Okay, you will not get quantum effects beyond 50 below. So below that, it's fine. You could have either, but beyond 50% is a true signature of quantum is what was prevalent. Okay, so we of course went on to show that this is not quite true. We can actually get 100% Hongo-Mandel visibility by using classical pulses with phase control. And so this is something, this is the experimental implementation, which, and so this is a 50% when you don't have phase control. And then this is our 100% dip when you do have phase control. Okay. And so we also went on to do this using single photons and again got the close to 100% dip. So classical pulses can be used to mimic 100% HOM. HOM is thus not a true signature of quantum, especially when it is used as a diagnostic for photon sources. So what next? I mean, this is of course something which tells you that something we have been believing so far needs to be re-examined. Yes. And so we said that, okay, we re-examine it in the sense that the HOM is not the final frontier. You have to do what is called the complementarity experiment, where you have to actually complete the HOM interferometer and do an interference experiment again to show the true difference between the classical and the quantum. So when you do this interference experiment in the HOM condition for both the classical and the quantum, and here I'll skip the details of how, but you can show that in the classical case, you will always be getting, a correlation, a normalized correlation of 0.5. Whereas in the quantum case, it will go down to 0.25. That is because in the quantum case, you actually have a superposition state. When you have the 2-0 minus 0-2 superposition state, and then, by using blockers in some way, by actually preventing the interference in one case and enabling it in the other, you can form a ratio where this superposition will matter. And in the classical case, it does not. And so the thing breaks down in the classical case. In the quantum case, however, complementarity can be used to differentiate between whether you had a true quantum source or a classical source. And so by completing this you can actually, you can say that complementarity is the true signature of quantum, whereas, we have been able to show 100% dip for the HOM effect using classical pulses. So classical pulses fail to demonstrate wave-particle duality without change in source setting, and photons follow the complementarity principle, exhibiting both particle-like and wave-like behavior. So you can see this is something, again, very fundamental, the complementarity principle, the wave and particle nature of light. This is what we are using as a diagnostic for the photon source itself. A perfect example of using something fundamental to comment on something which is very, very technologically oriented. So I want to know whether I have single photons. I will do an HOM experiment, but then maybe that is not enough. Now I have to do a complementarity experiment because that is the true signature of quantum. Finally, I come to quantum communication, where, of course, so I actually, as you can see, I've been going upwards in terms of the technological ramifications. And so I have dealt with quantum state estimation, I have dealt with quantum computing, dealt with quantum optics and a diagnostic tool. And now I'm dealing with quantum key distribution, which I think is the most quote unquote practical quantum technology, because in some sense, this is something which is actually available commercially as well. So this is something people are using, banks are using in other countries. And so something which really sees this ramification of fundamental quantum mechanics to quantum, technologies. Okay, so this is the most practical, and of course, I think you already know why it is important to do quantum key distribution. So there are all these, various strategic communications which will be lost if we will basically there'll be a catastrophe if we only believed in classical cryptography, because all said and done, classical cryptography, for instance, the RSA protocol, is based on the mathematical hardness of problems, and that is something which cannot go very far because we have these quantum computers and other advancements in computing which are coming up with new algorithms where the hardness can be broken. Okay, and so that is what we are looking at if we continue using the classical cryptography principles. So we need a solution which is quantum cryptography. I mean, of Shor's algorithm, which will break the RSA protocol. Okay, the factorization problem. So computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack, new algorithms for classical computers, realization of quantum computers. So my security should be independent of future advancements in computational power, new algorithms or new technology. That is, it should be future secure. And so this brings forth the need for quantum cryptography, where security is again based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And so that is where the quantum key distribution comes in. And we have heard some talks earlier which have gone into some of the details of some of the protocols. Just bear in mind that in order for Shor's algorithm to solve the factorization problem to be actually a problem for us, it will require 4,000 qubits and 100 million gates. Okay, and so we are clearly not there yet, but then it is going very fast. The progress in quantum computing and quantum communication, it's going very fast. And so just one second, yeah. So, it's going very fast. So we need to work on it today so that we don't compromise our security tomorrow. And so let's not get complacent by these numbers, which are not today's numbers, but maybe a few years down the line. Okay. And so in quantum communications, we are working on different areas at RRI, as Chiranjeevda mentioned. We are working on India's first project on satellite-based QKD. Quantum experiments using satellite technology. We are working on integrated photonics-based quantum communications under the ITPAR program, which is a collaboration with Italy, where we are going to have QKD on a chip, somewhat making QKD accessible to the common man like you and me. Then we have a project under the DST's Quest program, which is on quantum teleportation and repeater and relay technologies. Somebody really liked that, yeah, quantum teleportation. Right. So that was nice. Okay, so this is quantum teleportation, and then we have a project under the Center for Excellence in Quantum Technologies from MIT, which is on quantum and device-independent random number generation, which I won't get into the details of. Entanglement is needed in QKD so that we can go towards device-independent QKD, and that is something we are focusing on in our lab. Coming to our experiments, we've done several prepare and measure-based protocols where we use single photon states and the uncertainty principle for the security. So this is our BB84 demo experiment in 2017. Then we went on to do a novel implementation of the B92 experiment, which actually, we changed many things here so that we could increase the security and the key rate from the ones which have been done so far in literature. Okay, and this is something you can have a look at. And so to our knowledge till date, the best available B92 setup using SPDC source has reported a key rate of 31.6 kilohertz and a quantum bit error rate of 10.5% for 0.4 meters transmission. And here we have been able to generate, around 50 kilobits per second for 2 meters even, longer. And a QBER, which is restricted to 4.8%, which is the information theoretic security threshold for the B92 protocol. So if you do not have a QBER below that, then there's not much point because, then that is not a good candidate for a secure key. So this is something which involves information theory. And we have spent a lot of time and energy on coming up with experimental and theoretical, techniques to restrict this QBER to below this percent. Okay. Entanglement-based protocols we are performing with our dedicated polarization entangled photon sources on SPDC using entanglement measures as a source of security. This is a schematic of one of our sources, okay? And this is how it looks in the lab. This is where we have performed what is called the BBM92 protocol, which is again an entanglement-based QKD protocol. And this is a very nice entangled source that we have, which has a very high concurrence, as you can see, compared to the highest possible value. Okay. Now, this is a paper that, this actually has our experiment on B92, the one that I talked about, where we have this higher key rate and lower QBER and higher security. And it also introduces a very interesting simulation toolkit for QKD. In fact, this is our country's first reported end-to-end free space QKD experiment, which has been published in an internationally peer-reviewed journal. And of course, we're very happy at the forum that it got published in because, this actually summarizes the talk really. So while we deal with fundamental quantum phenomena, this is a very applied research in the same. Yeah. And so this is the paper, you can have a look. Regarding the toolkit, I wanted to spend a minute on that. So there are different types of, softwares which are available to simulate different aspects of QKD, okay? But then the point is that what we wanted was quick and precise simulation of the physical processes, okay? Considering realistic experimental imperfections. So simulation of the source, detection, background noise in more details, and applicability and generalization to all existing protocols. So what these guys do and others is they concentrate only on, the protocol without worrying about the fact that the protocol is actually to be done in realistic conditions. This actually involves optics and optomechanics, which are in no way ideal. Okay, so somehow these softwares are developed, of course, by software developers, and they need not be experimentalists. And so we had an advantage being experimentalists. And so when we came in and we realized that this doesn't exist. So if I actually use just this and come up with something, it will be much different from what will happen when I do the experiment. And experiments are real. They come with their real thrills and real imperfections, okay? And so everything needs to be simulated. And that is why we came up with an end-to-end simulation toolkit for QKD, which will give you realistic answers to your key rate, QBER, and other questions which you may have, okay? And which we call QKD Sim. And in fact, led to a lot of appreciation from the popular media. Coming to long-distance quantum communications, this is what it summarizes. Okay, so today's science fiction is tomorrow's science fact. When we first proposed the idea of doing satellite-based QKD several years ago, I would say 8 or 9 years ago to various agencies, it was treated as science fiction, really. Sending a single photon up and it'll be, something received by a satellite, which is hundreds of kilometers away, was not something which people really wanted to believe in because they felt it will never be possible, almost like science fiction. However, there was a demonstration from a neighboring country 3-4 years back. That is the only demonstration so far of satellite-based QKD, which actually changed this thought process in various sectors, including the agencies and scientists themselves. And so now it has become a science fact. Okay, and so that is how we do things, right? So we believe in what we do, and of course, then the whole community believes tomorrow. Okay, and so long distance QKD using satellites is somewhat in that domain. Used to be. And so why do we need satellites for QKD? I mean, we are doing fine. We are working. We have great results. Why do we need satellites? Well, we need satellites because just me and my student communicating with each other through QKD in the lab is not the aim of QKD, right? We want to secure communication for strategic purposes, and that will involve longer distances. So if I want to communicate with people in Kolkata using QKD, then of course that can't just happen by the simple means, because it's hundreds of kilometers away. So how do I do this distance barrier? If I wanted to have free space communication, then what I would need is line of sight. So two parties have to keep seeing each other, and beyond a point, the Earth's horizon is a problem. So demonstrations at best to maximum 300 kilometers. But then if I wanted to do fiber-based, then I would need to amplify the signal once in a while. That is what we do in classical communication, but that's not possible because of no cloning theorem. You cannot just copy an unknown quantum state. So you need to come up with out-of-the-box solutions. One of them is the repeater technology, which we are, as I said, investigating under the DST's Quest program, using entanglement relays and repeaters. And the other is using satellites for QKD. And so the idea is the satellite will act as a trusted node. We will communicate. So two parties will communicate with the satellite, and by certain actions, this will ensure that these two are now connected by a quantum link, a secure link, which otherwise would not be possible using free space or fiber. And so this is the idea of intercontinental quantum secured network. Okay. And so there are different possibilities using satellites and repeaters and so on. And this is the big picture that we are looking at as a community. So here we are with our project on satellite-based QKD. And then, once we do that, then this, station can then send these keys to different services, maybe through fiber networks. So we want to have a combination of fiber and satellite, and then at a later step, satellite to satellite, country to country, to have a global quantum communication network towards the quantum internet. And so this is the big picture towards these projects, and different countries with different possibilities are emerging. Okay. And so this is our project, which started, which is a collaboration between RRI and ISRO, started in 2017. Okay, and our aim is, of course, to establish secure quantum communication between two Indian ground stations using an Indian satellite as a trusted node. Okay, and in the process, we also aim to establish a secure quantum link between India and Canada, which would be of some 13,000 kilometers. Hopefully, that is something which will also work, and that would be a new distance record for satellite-based QKD. Okay, and so these are our portable ground stations at RRI. Okay, and so this is one of the telescope locations. And so this is our Alice and Bob station, which are separated by 50 meters, where we actually established the first free space quantum key distribution experiment in India early this year in January, February. Okay, and so this was entanglement-based QKD between two labs at RRI. And two buildings at RRI at this distance. And of course, the distance is something, if you come to RRI, you'll see that RRI actually is a very green place. Okay, so there are loads and loads of trees, which we all love. And so trees, however, have a problem because we can't see through trees. So we actually had to find locations where we will have clear line of sight. And so that is why these locations were selected. And this is actually where my lab is. Okay, and in fact, so this is our in-lab entanglement-based QKD, which was done last year, where we had very good key rates and QBA. And this is the first results from the atmospheric channel-based entanglement-based QKD, which was the first such demonstration in India, where we had reasonable key rates and also restricted to information theoretic security bound. And of course, after this demonstration, we of course had 2 to 2.5 months of lockdown. And so now we are back to these experiments where we are going to improve the key rates, and we're working on different aspects of security and so on and so forth. Okay. And so again, we were very, very lucky and privileged that a lot of acknowledgement from the popular media regarding this first free space quantum key distribution that we achieved at RRI. And of course, some of the members of the team who are still working on this, And, current situation is exactly summarized here. But then we are very enthusiastic because this is the first step towards even longer distances, finally culminating with satellite-based QKD. Okay, we were quoted as one of the 20 major success stories of DST in 2020. This particular work, and also the quantum state estimation work, actually the one that I talked about, and even the India Science, which is our nation's science channel, also recognized us as one of the top 10 innovations of 2020. Okay. With that, I think I'm on time. I would like to end my talk, and this is when we are, happier in terms of offline conference. This was our offline conference earlier last year, and I hope that we get back to this scenario soon in the future, because the future is bright and the future is in quantum. So thank you very much. I think I'll stop now.
Thank you, Urvashi, very much for your wonderful talk. Maybe you can stop the presentation mode and you can come out of that.
Yeah.
So there would be some questions on the chat box. Can you see the chat box?
Yes. Okay, is my lab operational? Yeah, for the last couple of weeks in lockdown. Okay.
Well, yeah, Shamsundar to everyone. Is it possible to get a higher dimension systems than Q quad? Okay, Qubit. Okay.
Yeah, sure. Of course, yes. Yeah, Q quad is just the 4-dimensional state. I mean, in fact, in principle, you can go to arbitrary dimensions, but then it will depend on the system that you're choosing, whether it will scale or not. In our case, we can easily go to, I would say, 10 dimensions without having much changes in our architecture. But if we want to go even higher, then we would have to bring about some changes. There are these systems which are based on orbital angular momentum, which actually are a parallel technique of doing higher dimensional systems in photons, where actually they start with an infinite dimensional space and then truncate it to finite. So, and then depending on the truncation level, they get different types of D, okay? And so each has its pros and cons. Ours is a bottom-up approach. That one is a top-down. And in the top-down, there can be leakages from higher dimensions. But then, the answer to that is definitely possible. And people have gone to really high in different systems. Yeah.
The next one is, so there will be a lot of students, so there will be some very basic questions.
Obviously. Those are the hard ones, yeah.
The entangled photons generated in spontaneous parametric down conversion method are called as signal and idler photon. Why such names?
Yeah, I mean, it's of course, this is something we should ask the people who named them this way. But my take on this is that the signal photon is the one which is kind of used for the experiment. And the idler photon is the one which we measure to herald the presence of the signal photon. So in some sense, the idler photon is quite idle in its participation in the experiment. It is just being measured as a herald for the signal. So in some sense, there is merit to this sort of naming to differentiate between the one which is participating actively in the experiment and the one which is just used as a trigger or as a proof that the other guy exists. So that is my take, but I don't know. I didn't name them, so.
Using Q-tricks or Q-quad will decrease size of the system, but is controlling a single Q-quad more challenging than Qubit? Say we need a superposition of 3 out of 4 states of a Q-quad, how difficult that would be?
Yeah, that is of course a very good question. And in fact, indeed, the answer to that is yes, it will be more challenging. Right? So as you increase the number of levels in a system, then they also need to be in a coherent superposition. So now you need a superposition of 4 levels instead of 2. So indeed, it will be more challenging. And in fact, the second question that you ask is about addressability. So am I being able to address the subsystems well? And so, yeah, these are all great questions. And that is why it is fun to work on them, because there are many challenges to overcome. And again, whether it is challenging, what is more and less challenging depends on the architecture of choice. And that is why it's an open field to come up with an architecture which is perhaps simpler, so that these challenges can be met and one can do interesting protocols.
Okay, the next one is difference between classical and quantum interference.
Yes. Yeah. So, classes, that is something I actually skipped here. So, of course, as you know, in case of what is interference, it is essentially telling you about the wave nature, right? of something. So now when you're talking about waves in a water tank or something, you have ripples. And so this also gives rise to interferences. You can see them. If you just have a water tank and if you just drop a coin, you will see ripples that will give rise to interference. So essentially that is your classical interference thing. But in quantum interference also, you will be able to see, you won't be able to distinguish between the patterns, but in quantum, you're dealing with one particle at a time. So in the quantum case, you're dealing with the wave nature of a single particle. So, and that is what I had skipped earlier. So at some level, we have a single particle, whereas we are actually seeing a manifestation of its wave nature in an interference experiment. So it is the wave particle duality that you see. And in a classical case, you're talking about the entire wave, which is not a single particle, right? So that would be one short answer to this question.
So the next one is Avinash Roy. In one of your slides, visibility was defined as the normalized difference between Imax and Imin. Is this definition specific to two-slit interference or works for multi-slit as well?
No, this is a general definition of visibility. It is for any interference. It's also something which will work seamlessly in a Mach-Zehnder. It's not restricted to slits either. So essentially, if you have an interferometer, you want to measure its visibility, then you want to find out what is the maximum possible, what is the minimum, and then this is a definition which transcends the genre, the architecture itself. Yeah.
How would you decrease error bit rate in recent Qubit experiments performed this year?
Sorry, but I'm actually interested in the second point. I'm not audible. Am I audible? Somebody has written after this question. Am I audible?
Yeah, you are on.
Okay, great. Yeah, because otherwise there is no point in answering anymore. Okay, so how would I decrease error but rate in recent Qubit?
Error bit rate, I think.
Sure. Yeah, of course. We are working in an atmospheric channel, right? So that is why lots of interesting things contribute to the error there. And so we are actually working on, I cannot tell you a lot more detail about exactly what are the error mitigation factors we are doing because we have a non-disclosure agreement with ISRO on this. So all I can tell you is that we are working on certain stabilization techniques so that naturally the error will go down and the key rate, because you see what we are interested in is the error corrected key rate, right? So if the error will go down, then naturally my throughput or output will be higher. And so there are certain optimization schemes that we are working on towards that. Yeah.
So what is the role of polarization in quantum interference? I think here it's more with detection, right?
Yes. So then in our case, we are actually using the polarization state. So see, polarization, so a single photon has many properties. So you can define it by its polarization state, you can define it by its spatial state, so many things, or timestamp, whatever. So we are choosing its polarization state and estimating that, right? So we are using polarization as the degree of freedom which we choose to estimate through quantum state interferography. So essentially, that is the role of polarization in that particular experiment. But if you have an interferometer, and if you have two parts in an interferometer, and they actually have different polarizations, then you won't have interference. So in some sense, if you go beyond the interferography experiment, maybe that is where this question is coming from. But then in another sense, that brings us to this quantum eraser and other experiments where you can actually change the polarization and see which path information and then interference going from one to the other. So if you have opposite polarizations, they don't interfere.
Yeah. So there is a question, can we create these arbitrary level system higher than qubits in other things like trapped ion, superconducting chips or NMRs?
Absolutely. And in fact, higher dimensional systems in all these systems have been realized. NMR being one of them, where definitely a lot of research is going on in qubits.
So, Urvashi, I have a question. So, would it be possible for you to screen your slides once again? There was one portion where you were showing this when we were showing the Hangu-Mandel effect, that you had an electrical circuit.
Yes.
That you got. Yeah. So you actually didn't dwell on it in much detail.
No, because the idea was to essentially give this holistic thing. I'm coming to that. You can ask the question in the meantime.
No. So what is it exactly? You do
this
that?
One, right?
Yes.
Yeah. So we have this, so essentially, as I said, what we have shown in theory is that you can have classical pulses okay, with perfect phase control. And then depending on the phase relationship these classical pulses share, you can actually have a control on the visibility of your homomandal interference. Okay, and so now here, so how do I get classical pulses? One way of doing it would be using a laser. You would say in my lab, it would be perhaps more conventional for me to use lasers to do this experiment. But then what you realize is that if you use lasers in the traditional Mach-Zehnder or any other interferometry, then lots of stabilization issues need to be also handled and so on. So that detracts us from the main focus, which is on classical pulses and phase control. So what we then went on to do is actually an electrical experiment. So here you have this, an arbitrary waveform generator. And so what we have done is we have essentially a Gaussian, modulated sine pulse. Okay, so one of them is the envelope function, and the other one is the actual signal. So that is why you can you can see where I'm coming to. So in order to have a phase relationship between these two, I can then play with it. So essentially, if an AWG is generating my pulses, so I can actually have them generated at the same time or out of phase or in phase. I can play with the phase relationship much better in a much more controlled way than I can do using optics, right? And so this is the arbitrary waveform generator, and this is of course your signal generator. And so here I have this, powered this circuit, not
distributor,
not circuit, the power distributor, which actually is mimicking a beam splitter. Okay.
Yeah.
And so then you can see that, and these are mixers. So essentially there is some up conversion, down conversion needed because I can't produce signals at the same.
So that in order to test in the digital oscilloscope, you need to.
Exactly. So down, because I don't have a gigahertz domain. So this is at the gigahertz. So I have an up conversion so that I can, this is the power splitter. Okay. So this is the power divider, power splitter. This is the complementarity. So here you can see the homomandal setup. And then, of course, I'm completing the Mach-Zehnder by using another power splitter, 50-50 power splitter and so on. And then again, the mixer to do the down conversion for the oscilloscope.
This was a very novel idea. Have other people also done it, or this was the first time?
No, this was the first time.
First time. Very good.
But then what people found it difficult to believe was this was the first time. So we had an interesting time discussing with referees because they said this should have happened, but no, it hasn't. So this was the first time that we showed that classical pulses with phase control. In fact, I'm sure I don't get tired of showing this graph. 100% literally, right?
Yeah.
So then essentially this just tells you that and in fact 100 is the number which kind of makes you sit up because 100 is what you would reach with a single photon. But then we can actually go from 50 to 100 seamlessly by having different phase relationships. So you can traverse this trajectory from 50 to 100. But of course, 100 is interesting because that is the single photon limit traditionally. Yeah.
Thanks very much. It's a good piece.
Yeah.
Very good piece.
Yeah. Thanks. So I'll stop sharing. Yeah.
Yes, okay. I think there are no further questions. It was a great talk. I learned a lot. Thank you, ma'am. Okay.
Yeah, sure. Yeah. So thanks very much. Yeah.
Yeah. All right. Thanks, Urvashi. Thanks a lot for.
Thanks, Chiranjeev. And of course, thanks to ISER for organizing this. I think it has been great.
Prashanta is there somewhere, I'm sure.
Yeah, he is omnipresent, right? But I'm sure he's hiding right now. So let's not catch him on his tea break, yes? But then thanks a lot. So I'll leave this call then.
Chiranjeev.
Yeah, okay, thank you. Yeah.
Sir, I will end this meeting for a minute and then start.
Yeah, so completely end it.
Yeah, because I have joined through browser. I want to join through
okay.
the app.